In chemistry, when we look at a balanced chemical equation, it's a lot like deciphering a recipe. If you think about making chocolate chip cookies or making brownies, a lot of times the recipe calls for a certain number of eggs. For instance, with brownies, it might be 2 eggs if you want fudge-like brownies, 3 eggs if you want cake-like brownies. Me, myself, I'm partial to the fudge-like brownies, so I usually go for 2. But that's beside the point here. The point is, with a recipe like that, it's very easy to pick out individual particles of the ingredients that you need. But when we deal with chemical equations and reactions where our ingredients are very, very small, they react in the same sort of way. They react on a particle by particle basis. So if we look at hydrogen plus oxygen yielding water, and we were able to look at them on a molecular level, we'd probably see something like the following. So as you can see, our 2 molecules of diatomic hydrogen have 2 single bonded hydrogens connected to one another, and our single molecule of diatomic oxygen has 2 atoms of oxygen that are double bonded together. And if you're not sure why it's a double bond, you can do the Lewis structure for it and see that it's filling the valence shell for oxygen that way. But when we look at the product that's made, we see that according to the balanced equation, there are 2 molecules of water. And when we look at the structure, we see that these original building block atoms have broken their original bonds, become independent atoms, and now reformed new bonds to create our 2 different water molecules. And of course, the atoms are conserved according to the law of conservation. So when we think about how can we actually do this, we can't count individual hydrogen molecules and oxygen molecules. We need to still be able to react them on this particle by particle basis relationship, but we can't measure that out in a laboratory. But we can measure things like mass, we can measure things like volume in a laboratory. And because we can establish a relationship between the mass of particles and the number of particles, and in the case of gases, the volume of a gas and the number of particles, i.e. the moles of a gas, we are able to carry out these reactions, these recipes, using methods that we can get in the laboratory. When we're trying to determine just how much of a certain substance we either need or can produce based on another substance involved in the reaction, this is something called stoichiometry. Stoichiometry is important to us in chemistry because as we do our reactions, we want to use methods that are going to generate as little waste as possible, present as few hazards as possible. So if you minimize hazardous materials, that's always a good thing. We want to maximize the amount of product that we can get. And we also want to find a method that's going to be efficient. And stoichiometry helps us with all of these things. So the process of stoichiometry involves a number of steps. And the first thing that we need to know is what is it we're starting with and what is it that we are trying to find. And so let's take, for example, that we are going to work with and say that we've got 40 liters of hydrogen gas, and we'll assume that that's at STP, standard temperature and pressure, and that we want to determine how many grams of water can be produced if we start this reaction with 40 liters of hydrogen. So the first thing that we need to do is we're going to carry out a series of conversions, and we're going to go work our way stepwise from one unit to the next until we get to units of grams of water. We first have to start with what we're given, which is liters of hydrogen. So we're going to start with the volume in this case. The next thing we need to do is we need to get this initial quantity of hydrogen into moles, because when we have a substance expressed in moles, then we can compare one substance to another in terms of how many particles are there. So we've got to get to those mole units. And so in this case, since we're starting with liters and we're going to moles, we need to use the molar volume, which is 22.4 liters for every 1 mole of gas, so long as we're at STP, and that's what we said we were going to assume here. Now you'll notice that when I used that molar volume conversion factor, I set it up so that the 22.4 liters of hydrogen was on the bottom. And I did that because the liters of hydrogen need to be able to cancel out. leaving us with moles of hydrogen on the top. So now we are at moles of hydrogen, which is our starting material. And now we need to look to our recipe, our equation, and determine what's the relationship between this particular reactant and the product that we're looking for. Right? And in this case, we have 2 moles of hydrogen for 2 moles of water. So essentially it's a 1-to-1 ratio. But the next step that we write is going to be a ratio of those moles. The final material will go on top, the starting material will go on the bottom. Note again that the units are moles, top and bottom, but on top it's moles of water, on the bottom it's moles of hydrogen. It's important in stoichiometry to not only write the units of measure, the liters and the moles, but also the formula so you can keep straight what it is that you're talking about. So the moles of hydrogen will factor, and now we're talking in terms of moles of our product, of water. And we're almost there. We want to get to grams of water. So whenever we want to convert from moles to grams, we need to use the molar mass. And so if we look at the formula for water, H2O, 2 hydrogens plus the mass of 1 oxygen to 3 sig figs would give us a mass of 18.0 grams for every 1 mole of water. And we can see that the moles of water cancel out. So now we have worked our way from our initial amount. We've gone through and used a series of equivalent values, conversion factors, to take this initial quantity and convert it to what it would be equivalent to in grams of water. So that all that remains now to do with our stoichiometry is multiply our numerators, multiply your denominators, and then divide the two and come up with your answer. Now, when you do the math in terms of sig figs, all right, the initial value, we always consider that. That's considered a measurement, and it has some level of uncertainty built into it. All the other values, though, okay, are 22.4 liters for every 1 mole. That's considered an exact value. We don't use it for sig figs. The mole ratio, those numbers come from the whole number coefficients in the balanced equation. So they're considered exact. We don't consider them. Molar mass, because we are using rounded off values from the periodic table, we are going to want to consider those. So between these two, each of them have 3 sig figs. So our final answer should have 3 significant figures. And in this case, your answer comes out to 32.1 grams of H2O. Stoichiometry is a very useful tool to use when you are trying to design a process to maximize your yield or determine a very specific set of conditions while at the same time minimizing waste and helping you to efficiently plan out just how much of materials you're going to need. So a lot of times stoichiometry problems, we might be given a starting material, a reactant, and asked to figure out how much product can that produce. But we can also use stoichiometry in the reverse direction. We can start by knowing how much of a certain product we want to produce or need to produce, and then backtrack and figure out how much reactant do I need. Kind of like going back to the sandwich analogy, if I need to make 15 sandwiches, how many slices of bread am I going to need to start from? And so you're starting at the end and working backwards. But the process is exactly the same. So let's say we have 100 grams of ammonia is what we are after. And we want to know how much or what volume of hydrogen gas are we going to need in order to generate that 100 grams of ammonia. So the process that we're going to use is exactly the same process that we've looked at in other stoichiometry problems. We're going to start with the given amount that we are given in the problem. And the first thing that we need to do is we need to convert the given quantity that we have into units of moles, because that's what allows us to use our balanced equation to make the relationship between the starting material and the final material. So to go from grams to moles of ammonia, we need to use ammonia's molar mass. We set up the molar mass so that the grams of ammonia are on the bottom. The next step is to convert from moles of our starting material to moles of our final material. And so this is our mole ratio step. So again, I would suggest start by writing in your mole units and the formulas. Don't worry about the numbers just yet. Get those units set up so that you can see where the mole units are going to factor out. But then go to your balanced equation and look at the coefficient for hydrogen, which is 3, and the coefficient for ammonia, which is 2. Now that we are in moles of the final material, we can go that last step, and in this case it is to go to liters of hydrogen. And so, assuming that we are at standard temperature and pressure conditions, unless you're told specifically otherwise, it's safe to assume that you are at STP when dealing with gases. To go from moles to volume, we use the molar volume for a gas at STP, which is 22.4 liters for every 1 mole of gas. Now that we've converted our quantity into units of liters of hydrogen, it's time to do the math. And so we multiply across our numerators, multiply across our denominators, then divide the two. And the answer that we get is 197.6 liters. Again, looking at significant figures, we always consider the initial value, the measured value we're given. That has 3 significant figures. The molar masses we want to consider as well. So we've got 3 in the 17.0. And the rest of the values that we have here are considered exact values, so we're not going to consider them. So our final answer should be reported with 3 significant figures, which would make our final answer 198 liters of hydrogen. So whatever kind of stoichiometry problem you are asked to solve, the same basic steps are used. The first thing is to convert from your given units, be it mass, be it atoms or molecules or volume, convert that to moles. Then use the mole ratio, which is based on the coefficients in the balanced equation, to convert from starting material to final material. And the last step will then be to convert to whatever the desired units are, again using those coefficients or the conversion factors of molar mass, Avogadro's number, or molar volume, depending on what you're asked to solve for.